Problem 34 is a multi-period production problem. We have production goals for 4 months, April through July, but we've got limited capability. We cannot meet those goals with regular production during those months. Alternate ways to meet the goal: we can produce up to 30 engines per month in January, February, and March and hold them in inventory for a cost of $50 per engine per month. Alternatively, we can manufacture up to 20 engines per month in overtime, but that's going to cost $400 per engine. So what we are looking for is the way to meet our production goals at the lowest possible cost. Now, this is a multi-period production problem, so let's take a look at our production network. In any given month, we have regular production, overtime production, items coming in from the previous month through the warehouse, and items going back into the warehouse for use in future periods. We also have demand for each period. W sub I is the number of engines to put in the warehouse in a period, and we're going to define two constants. One will be the demand each period, and the second will be the capacity. Again, D and C are both constants. They are not decision variables. Where do they show up on this model? Well, we've got demand and the capacity. We will use those strictly in a capacity constraint on the regular production. Our objective, we want to minimize the cost, and we have two costs in this model. One is the cost of storing engines in the warehouse, $50 per month per engine, and the second is going to be the cost of overtime production, $400 per engine. We have regular production, but that is not, cost for that is not given to us, and so our objective is to minimize cost, and we're going to figure the cost by summing for all period i's $50 times W sub I, number of engines that are going into warehouse each period, plus 400 times O sub I, the number of engines that are produced in overtime during each period. Several different ways to write this objective function out, but that's probably the most compact. Constraints. We're going to have several different types of constraints, but the first constraint we're going to look at is the one that gives us the structure of the network. That's the balance of flow constraint. And to build the balance of flow constraint, once again, we have to take a look at the total supply and the total demand. If we add up the total production capability, we're going to find that that does exceed the production goals. So our supply in this problem is greater than demand, which means our balance of flow constraints will all be greater than or equal to constraints. And for any given month, our balance of flow constraint will be regular production plus overtime production plus warehouse from the previous period. Outflows will be warehouse for the current period. Relationship greater than or equal to D sub I is the production goal or the demand for that period. So let's take a look at one period, period 4. For period 4, regular production plus overtime production for period 4 plus what came into period 4 from the warehouse from the previous period, that's W3, minus what we're putting into the warehouse this period, W4, greater than or equal to the demand for period 4. And the demand for period 4 is 60 units. We can build that balance of flow constraint for any period, and we'll need to build the balance of flow constraint for all 7 periods. Every one will follow this pattern. Additional constraints that we have. Regular production for every period has to be less than our capacity for the period. So for instance, for period 4, April, our regular production capability is 40 engines. Our 4 would have to be less than or equal to 40. Overtime production for every period has to be less than or equal to 20. We can only produce 20 engines in overtime during those periods in which they can be used. And our final constraint, non-negativity, R sub I, O sub I, W sub I has to be greater than 0 for every period I. Now, taking this into our spreadsheet, we've got decision variables for regular production, overtime production, and warehouse production, or warehouse storage. Notice that I am allowing overtime production in every period. It's very likely that we're not going to require overtime production during those periods. I'm going to calculate the inflow and the outflow for each period. Inflow minus outflow will give me my net flow for each period. Inflow. I have nothing for inflow during the first period. So let's drop down to the second period. Inflow, that's incorrect. Inflow for the first period will be regular production plus overtime production. Outflow will be the warehouse. And the net flow will be equal to inflow minus outflow. I'm going to copy these three down to the second row. I have to make one change to my inflow on the second period because I also have warehouse from the previous period coming in. Make that change, I can carry this all the way down. Now the next thing I need to do is I need to total regular production, overtime production, and warehouse so that I can get my objective function. My total cost is going to be the sum product of these sums and the unit cost. Now let's bring Solver up. Reset all. Target cell will be my total cost. I want to minimize that. Changing cells will be my decision variables. Constraints. Balance of flow, the left-hand side, needs to be greater than or equal to the production goals for each period. Regular production has to be less than or equal to the capacity. Overtime production has to be less than or equal to the overtime capacity. Linear, non-negative, and I can solve my problem. I end up with a total cost of $34,500.